Hello, my name is Zuriaga Puig, and today I will talk to you about the work that I've been doing with my collaboration, Viviana Gamaldi, Daniele Gaggero, Tomás Lacroix, and Miguel Ángel Sánchez Conde, about the multi-TeV dark matter density in the inner Milky Way halo, spectral and dynamical constraints. So first, this work is based on indirect detection dark matter, especially in WIMPs. So in our case, we are assuming that the dark matters annihilate in some different channels, could be quarks, bosons, leptons. In our case, we are focusing on the Z channel, and these particles can produce secondary particles, gamma ray neutrinos or cosmic rays that we can observe. In our case, the base of this work is the gamma rays part. So the motivation first is the TeV cutoff detected by Hess. There are two main works within this hypothesis, which is the Belikov et al. And Zembranos et al., which assuming the region about 0.11 degrees in the galactic center, this Hess J1745 to 90, which corresponds to Sagittarius A star. Well, assuming that the flux observed is a combination of dark matter plus a power law background, more or less, and assuming the thermal Rayleigh cross-section, some results can be extracted. The first one is that they can be set constraints on the dark matter density profile. More specifically, that the boost factor needed with respect to the benchmark Navarro-Franken-White is about 1,000. So the idea is the possible explanation by an enhancement of the dark matter density profiles. So the outline of this work is, first, we will see 5 regions of interest observed by Hess. We will see what is the spectral analysis components of the gamma ray part for the background model for the 5 regions and the dark matter density profiles considered. Then we will see the J factors that we have obtained from them, and then the constraint that can be extracted, both in the external dark matter profile and the internal innermost dark matter profile. So the galactic center observed by Hess. So this work is focused on 5 different regions, these 5 publications by Hess collaboration. And we call them the following ones. So first we have the very near region, the BIR, which is the same one as the same region as before, this 0.11 degrees, corresponding to the green dot in the center of the picture. Then we have the ridge, which is this gray region comprising the galactic center, the diffuse region also, which is this blue disk surrounding it, starting at 0.15 degrees, more or less. Then we have the Hess halo, what I call halo, which is this red part getting up to 1 degree from the galactic center. And finally, the inner galaxy survey, which is up to 3 degrees. So first, as I said, the indirect detection WIMPs with gamma rays. So the dark matter Elysium produces gamma rays. This is the main idea. In this case, following this formula here, I will talk to you about more or less what is the main part. First, we have the channels within happens this annihilation. In this case, we are only focusing on the Z channel, as I said before. And then we have this part here, this DND, which is the particle physics parts. And in this case, I am using the Chirelli code to extract the flux. And finally, we have the J factor, which is where the information about the dark matter density profile is located, which is basically the integral of the dark matter density profile squared along the line of sight, as we can see from this picture. First, one is the first components of this analysis, of course, the dark matter density profile. In this work, we are using several density models coming from simulation and both observations. So in this case, these solid lines here are coming from simulations, Milky Way-like halos. Dark matter it's only for n-body simulation, and the rest of them are hydrodynamical simulations. Then Macmillan 17 and Benito 20 are models coming from observations, mostly rotation curves, for example, for the case of Benito 20. And then these are the profiles that we are using. The main idea is to use these Navarro-Franken-White generalized profiles, which has different parameters. The most important one in our case is this gamma parameter, which is how is the slope when in the inner regions, how is this slope right here. And the second most important part of this analysis is, of course, the background model. I am using the Dragon model to compute how is this background model existing in the diffuse emission. So one source of uncertainty in this astrophysical background diffuse model, both the diffuse and also the several point sources within the regions. This diffuse emission is mainly due to the presence of charged cosmic rays, C, confined in the galaxy by the turbulent field. And this sea of cosmic ray can interact with this gas and low energy photons emitting gamma ray flux up to 2 eV scales that we can indeed observe. And the main interactions that are in this code, in this Dragon code, are synchrotron, Bestellium, inverse Compton, and the neutral pion decay. And I will use Dragon, both, and Hermes to get the spectral shape of the emission, leaving as a free parameter this B squared parameter, which is a normalizing factor left in each region. Then for the regions that I showed before, these ones here, the green and the blue, the very neat region and diffuse, this is the flux observed by Hess and the different fits that we have made. The most important number here for these parameters is, basically, of course, the dark matter mass given by the fit, by the best fit, which is around 36 TeVs. And then, of course, the J factor, which gives the information about how is the density, how is the dark matter density profile, which is this number. And comparing it with the dark matter only simulation with the Navarro benchmark Navarro frequent wave profile, we see that we need around 1,000 for both the very near region and reach in order to explain the curve. So in this plot right here, the red line is coming basically for the dark matter annihilation flux, and this green line is the background flux. And in the reach, we have, more or less the same region. As we can see here in the very near region, we have the number of the mass, and in the reach, we don't, because we have left fixed this number for the very near region for the rest of the regions that we have. However, we have also checked what happens if we leave it as a free parameter, for example, for the reach, and we more or less obtain the same results. For the diffuse region, the diffuse is, I remind you, this blue disk surrounding the very near region, which is starting around 0.15 degrees. In this case, doing the same as before, sweeping the parameter, the J factor, and both the renormalization of the background, we obtain the best fit, which is located right here, this red dot, and also this 2 sigma region, which is in gray. I have also showed here the reach best fit parameter to see that we have some or less some coincidence and correspondence with the rest of the regions. Then for the halo and the IGS, the halo is this red region surrounding the rest of them. These Hess collaboration papers basically said that the source and the background region, more or less, the signal is the same. So in our case, we can only extract upper limits for the parameters. And indeed, this is what we have. So this will be the 2 sigma upper limits, this gray region here, and the rest of it is excluded. This is for the halo and for the IGS as well. This is will be the region that I'm calling IGS, this orange region. And this is the final results of the spectral analysis, which we can see here. I'm plotting the J factor versus the galactic latitude of the galactic center. So each horizontal line, colored line, this green, blue, red, yellow, red and orange are the ones coming from the fitted values of the gamma ray part. I am also showing the J factors and the range of the values of the J factors for the dark matter only, dark matter only density profile in the Benito 20. And we can see here that we need some kind of enhancement, or the best or the peaked part of the Benito 20 could explain this line right here. And we will see what are the constraints that we can obtain from them. So now we will see the constraints of the dark matter density profile coming from the simulation and dynamical observation, the different profiles that I have shown, and also the S2 star orbit. So the density profile, as I said, we need dark matter density profiles well described in order to compute the J factors. And so we will use different models coming from simulation and observation. And given the uncertainties in the galactic center, we use a wide range of models. Actually, we use Caspi profiles and Core profiles and everything in between. And in this case is this local dark matter density versus the parameter gamma, this slope of the profile for the different dark matter density profile that we use. And this is the main results using the generalized Navarro frequent wave profile. This is the extrapolation of the external profile to the inner region, just as it is, this formula as it is. So computing the J factor for the different models and models, the matter density profiles, comparing it with the fitted value, we obtain that around gamma equals to 1.3, more or less, we have that both Benito 20 and Macmillan crosses this fitted value for the very near region. However, for the rich, diffuse, and halo, we do not have the same correspondence. Well, the idea of this is that since we are using a very conservative approach, we can only exclude the J factors or the dark matter density models, in our case, dark matter density profiles, that gives a gamma ray greater than the one observed by Hess. So in our case, all of the points and lines that are above these horizontal lines are excluded. So the allowed region would be this gamma 1.3 here, not this part of here from Macmillan. Then what happens if we have an inner dark matter spike? So in our case, we're using 3 different spikes that we can more or less compute and the shape of the spikes. And we have the adiabatic spike coming from gondola and silk, basically. Then we have what happens if the adiabatic spike also takes into account the interaction with the stars, which is this dotted line right here. So this dashed line, the first one, is the most cuspy spike possible, which is the adiabatic. Then we have the stars spike, which flattens a little bit the spike, as we can see. And then the instantaneous spike, which is the extreme case of the instantaneous form of the spike, which is this dot dash line right here. We have done the same. We have computed how it is the profile for each of our models, or the matter density models. And for the case of the adiabatic spike, we need to assume the adiabatic growth of the supermassive black hole, Sagittarius A star, the central position of Sagittarius A star during all of its formation, and that no major mergers has happened during the last 10 gigayears, more or less. And as we can see here from the very near region part here, we can exclude almost every single model because the J factors computed are way above the ones given by the gamma ray part. However, for the rich, diffuse, and halo, we cannot exclude, we cannot have the same exclusion region, and that is because this region, the rich and the diffuse and the halo as well, do not observe the spike. The spike is mainly around 0.15 degrees. The spatial range of the spatial region is 0.15 degrees. So the rich and the diffuse do not observe the very center of the galaxy. Well, they mask this region. So we cannot see the spike. And indeed, this is what observed. So the fitted values or the upper limit values do not give the same value for the computed ones. This is for the spike stars part. This is adiabatic part, also using scattering of dark matter particles of stars and the heating of dark matter particles. Because of that, we have the flattening of the spike, as I have shown before. So in our case, our crossing point is around gamma, around 0.8, as we can see here. And finally, instantaneous spike, which is the extreme case of the instantaneous formation of the supermassive black hole. We have that the crossing point is about 1.2. So above these lines is excluded. So this is the a slide to show the best profile. So Navarro-Franken-White with 1.3, stars spike with 0.8, and instantaneous with 1.2. We can see that they are quite similar in shape, unless this little part right here. I am also showing the different very near region, the rich and diffuse, the different regions that we have observed in order to see it better. And the idea is above these profiles, since the J factor would be bigger than the ones given by the gamma ray part, they are excluded. So this would be the shape of the maximum shape allowed by the gamma ray part. We can do the same idea, but using the S2 star. This is dynamical constraints coming from the orbit of the S2 star. And this is independent of any particular dark matter theory. So we do not need to assume WIMPs annihilating into dark matter or anything like that. So in our case, we can constrain more or less what is the enclosed mass, extended the closed mass within the S2 star. Following these papers by Gravity and Doe et al., I'm showing here the radius of the spike versus the gamma, the slope of the profile. And this is the different excluded regions right here. And these are the dark matter density profiles, well, the spike radius given by the different models. And around 0.7, 0.8 for the case of the Macmillan 17 and using Benito 20 as a base model, we have around 0.6. We can exclude the spikes given by the profiles with greater slope, with greater gamma. I'm showing the same as before, but now only with the mass, with the integrated mass. So in our case, this is the integrated mass of the halo, and this is the radius from the galactic center. Of course, there will be the excluded region of the excluded regions. And every time we cross this line, of course, we are excluding the model. In the adiabatic spike, is the same constraint as before, as I have shown before, the same models. And for the stars spike, nothing can be constrained. Actually, for the stars spike and the different approaches that I'm using, giving the stars spike and also the instantaneous spike. Of course, the Navarro effect while generalized also do not reach this excluded region right here. So the final conclusions are that the fitted value for the TeV WIMP particle is around 36 TeVs, assuming a thermal Rayleigh cross-section of about 2.2, 10 to the minus 26. We have a conservative approach, so the idea is that we can only exclude all the profiles with a J factor greater than the fitted values. And using the diffuse region, we obtain that if a dark matter spike exists in the galactic center, no matter if it is adiabatic or with stars or instantaneous, it is required to have the angular dimension of around 0.15 degrees, right here, what I'm showing here. And so a future analysis is required because with the gamma rays, we could be able to extract the shape if, of course, that matter is WIMPs and annihilate into gamma rays. We should be able to resolve what is the shape of the spike, if there is any spike to begin with, of course. And these are the final constraints. So we have, with the Navarro-Franken-Wald generalized, excluded at around gamma 0.36, more or less. The adiabatic is completely excluded. The stars spike is 0.8, more or less, and the instantaneous is around 1.2. And using the S2 star, we can see that only the adiabatic can be excluded at around 0.6, greater than 0.6 would be the excluded value for the gamma. And that would be all.